Okay, that's it. That see my right. Oh man, this now is 3 minutes to can't can't how how well I'm impressed. I want to say really how speechless I am. Yes, how amazed I am that as you can hear finally managed to implement a DP dynamic programming coding. This is really quite an achievement. 7 years plus in coding. I actually already heard of dynamic programming maybe the last year of my university. Yeah, during my undergraduate. Uh, at that time, I I had some friends who are they are freshmen and they are all in computer science school. They major in computer, and I've heard them talking about ever since my last year of uni, which is in I never really got into or yeah, I never really get the chance to implement or think of a dynamic programming solution or algorithm. And they switched, and the night is really milestone journey because yeah, this is not really an update to check to Hallelujah Digital or other. I will be posting those projects in next stream, but just share. I just want to share how grateful I am. I am really satisfied this accomplishment. I mean, like this is really nothing compared to grammars and those PS students really know how to but for me this is I never I never really thought that I get get to him. I mean, like I don't want to I don't want to talk about how I ended up not picking major. Let's save that story for another day. But right now I just want to save here the moment that I meant this. And well, you can probably see in right here runtime or free usage is not a very clever yeah, not a very efficient one. I I am put here maybe in the last quarter.
quartile,
Quartile. Quartile. Yes, the W. Anyway, yeah, I think I'm in the last quartile of this distribution. I didn't I don't care much. I mean, like, let's go to the okay, problem for uh daily code challenge. 5th of Jan- Yeah, I just want to share this, commemorate, and I know it's not. I think it's a very terrible uh not algorithm, but yeah, let's just say really terrible producing algorithm for this solution. But and I've been staring this rotating late code coin quite some time just now, and when I finished or I got accepted, I'm really happy. I was really happy. I really I couldn't help myself tell her that I've never really thought that this day would come to my. Okay, and this really proves that I am improving and can improve. I can better and better in coding, in competitive programming, or even preparation for my ambition. I will tell my, but okay, let's go to the solution. Before that, I step step those. Yeah, yeah. Really, there are no drop frames. Yes, it means that all the frames, all the all the yeah, all the moment that you see on screen are all captured and streamed. Guessing that means when there is no drop frames. Uh, okay, and so I think everything is fine from OBS. Close this, or let me screenshot this. Okay, okay, yes. Now I screen, but it also, and never mind. I mean, like, I screenshot it just at the right moment when the sparkle, when the bling appears here. Okay, close this, and now so actually the problem is this. Go to the definition. Uh, we are given an integer array, then we need to find the length of the longest strictly increasing sub. here is a tooltip what a subsequence is. It's actually an array that you it can be it is derived from another array by deleting elements of the initial array, but we are not allowed to change the order of any arrays. I mean, like, sorry, any elements that are remaining, or yeah, they are remaining. Yeah, cannot change. I mean, any order of the. So, for example, uh, they gave this array of nums, and the output should be 4. Why? Because the longest increasing subsequence is 2. Then let's erase this 5 uh, number in the sequence or in 3, and we also take 7 because 7 is strictly increasing compared to previous number, which is 3. And when we got to 101, it's also an increasing number, strictly, because it's higher than 7. So but when we get to the last element of initial array, 18 is not increasing from 101. So actually the longest increasing subsequence is 2, 3, 7, and 1. Then there are a couple of examples afterward. And uh if you see my test result, there are 4 cases normally or initially in LeetCode. The example cases are the ones in test result. So I add my own test case, or maybe I should not say this is my own test, because this is actually the test case that I failed during my initial go to all submissions. You can see I already submitted 3 times before accepted one. The third one is the one that has runtime, that was runtime error, is was not really on purpose. I accidentally pressed the shortcut for submit, so I got runtime error. The compile error is actually, I think this was because I was using too much memory, so ended up in a compile error situation. And the last one, wrong answer. Let's see what I submitted. So yeah, this is what I submitted. I naively go to go through each element one by one, and then for each element from from the beginning until the element before the current element that we are looping, uh we we push the current element if the current element is bigger than the last element in the subsequences of the current of each position. So my idea is, in each position, like the zero index, the first index, second index, and so on, for each index I keep track the subsequences that are possible. I mean, my intuition is correct. I mean, it's heading in the correct direction. I really believe that I already had the slightly correct in, but the implementation uh is still far from right. So here I check whether each element, like for example, let's go through this algorithm, or yeah, algorithm, the falsy algorithm for several elements. Like for example, we go to the first element, it's 5. We put an array with 5 inside. with only 5 as the subsequence in the 0 index. Yeah, store it as the sequence index. Then for j equals 0, j less than I is still 0. So actually this loop is not run for the first I. Now we move to the second I plus plus. I now is 1. The first index is in our initial array is 7. So again, we initialize the subsequence in this index. We initialize it to be array of 7. I mean like array containing only 7. And then we look from the beginning, from the first element until the element before our current I index element. So for example, if right now the I is 1, which we are here, we look from 5, and if we look at we check if the I element, which is 7, if it's larger for its for every subsequences in the previous index, if the last element in that subsequence in each subsequent is less than the current I element, we push the current I element to the subsequence. Like for example here, we know that we initialize the 0 subsequent to be an array with only 5, but because we look here, we and 7 is larger than the last element of the this subsequence, which is actually the first element as well, which is 5. So 7 bigger than 5, or 5 is less than 7. We push 7 as in the subsequence in the of the 0th index. And what about this one? This So in case that the number I is actually or the current I element is actually larger, or no. If it's not, yeah, if it's not less than the last element, let's say it's larger or equal. And also we check whether in the subsequences, or like it's wait. No, I'm pretty sure this is a very weird. I don't know what I was doing here. I like this is I slice the subsequence array in the J index from the first element to the second last element. If and then I check whether every element is less than now. If every element is less than the current I, uh, I update. Oh, okay. So what I was trying to do here is to get the last element in each subsequence as small as possible. So if actually the current I is bigger than all those all those all those elements in the subsequences before the last element, but but our last element is actually bigger or equal to the current I element, we substitute the last element in the subsequence with the current I element. Yeah, this is because I want to minimize the last element in the subsequent. And if uh okay, wait uh, okay and finally, if the length of subsequence actually larger than the current answer, we updated our answer. We the length of the subsequence with bigger length. compared to the answer. And yeah, actually we we did uh so here. We passed half of the test cases, but unfortunately we failed here. Why we fail? Because in this solution, when we go to when we go to here, yeah, when I equals 0, 1, 5, and then um, we try to try to loop over the previous element and see whether 2 is bigger than the last element in the subsequence of each index. Then we yeah, you know lah, we run through this, but actually 2 is very small. It's actually only larger than minus 24, but we are not actually comparing 2 to minus 24. Remember that we store a list of numbers. We call it subsequence in each index. So when when for the two for the subsequence in index 2, this one is the subsequent is actually like minus 24 and then 12 and then 13. Why? Because we already go through these two elements, and 12 is bigger than minus 24, 13 is also bigger than 12. So the subsequence for this ith index, or I mean for this second uh, index, it's actually minus 24, 12, and 13. So 2, although is actually used in the largest or the yeah, the largest subsequent increasing strictly increasing subsequence, our algorithm right now it fails to recognize that. So uh actually 2 is used, I mean like the subsequence in this index is later. If we are continuing this algorithm until the last element, the subsequent here is 2, 3, then 5, 6, and then 35, which results in 5 5 length, or like 5 number subsequence with the length of size of 5. There are 5 numbers: 2, 3, 5, 6, 35. But the correct answer for this this array of numbers is actually a size of 6 subsequence. That is starting from minus 24, 2, 3, 5, 6, and then 36 elements. So okay, this is a wrong answer. We already settled or agreed on that. It's already stated here. And the compile error, okay, yeah, this one, no, I think this one is where I gently press runtime error. Ah, yes, yes. Oh, I I mixed. I think I got it the other way around. Uh, the runtime error is actually the one that I think my algorithm was running out of memory. And I think this is quite I mean like I'm also uh I think this is a desperate solution. I cannot think of anything else, and I try to make subsequence. I mean like I try to take note of each possible subsequence every time we move to a new element. Like for example, and I fail, or the algorithm was running out of memory because I mean in this test case, which is, well, I didn't confirm this, but from uh I mean like from slight look at this array, you can guess this array contains uh, r- uh, uh a series of numbers that that are that is increasing by one every element, and the number of elements here is 2500. It's equal to the limit that, or to the constraints of the problem. So yeah, I failed by running out of memory here, because stupidly I just like, let me do a three element example. Okay, so when we go to the first element, it's one, we push one, an array containing one as subsequences, and then we go to the subsequence. Yeah, we go through all the subsequence except the last one that we just pushed, and we see whether uh whether the current I is bigger than the last subsequence of the last element in each subsequence. Yeah, if number the current element is larger than the last element of each subsequent, we push that. I mean, like, we not only push the number into that subsequence, but we push a new subsequent. Yeah, we push a new subsequent. Wait a sec. Happen. Well, this is interesting because the limit here is the length of the subsequences. But now here inside the loop, we also push a new element. Well, I need to investigate what happened here, but yeah, actually this is why I think it got std bed alloc error, runtime error. I think this stands for allocation. Yeah, the program doesn't have enough memory, didn't have enough memory to allocate this kind of array, because uh every time there's a new element, we check the element, we compare the current element to every possible subsequences that we already created before. And yeah, quite bad. And but if I think if we have a very uh a big I mean, like, a very big memory, a computer with a very big memory, like it's like so big that I think this program can run. And yeah, I don't know for how long until it finish running, but I think it will run. Anyway, now we got to the accepted solution. And if you see my the tabs that I open here, two of them as have dynamic programming as their title. And because I didn't look at the hint or the topics, I just kind of remember that this kind of thing, we can store something, and then we refer to what we stored previously, and then we uh using some kind of logic by checking what we have stored before, and then what is our current uh state that we want to calculate the outcome for this current state. I mean, like, using those two things, the situations that we have stored for each past no, the outcomes, yeah, the outcomes of past of yeah of the previous situations, and then the current situation, by using these two things, and then applying it with some logic, we can calculate each position, it's the outcome of each position, particularly for a position or a state of the whole array. Yeah, because I don't know, it's just I don't I, d- yeah, just like initially in the beginning of this stream, I actually don't know how to uh implement dynamic programming, or I don't even recognize this. I mean, I couldn't even recall the term dynamic programming when I started this problem, started to solve this problem. But yeah, long I mean like somewhere or sometime after I tried to think of the solution, I just recall that the way I think of like my intuition of storing the s- outcome from the previous situation and then using it to calculate some of the current situation. I remember, yeah, just from days of my university year. Uh, yeah, that is what they call dynamic programming. Yeah, and then I know that uh I know that I lack the not the mindset, but I lack the intuition, or like the 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 thinking process. Yes, I lack the thinking process to come up with dynamic programming. So I need to see some people explain dynamic programming and probably show me a few examples of dynamic programming. And here this channel by Eric To, I subscribe to him, although there has not been any new update past few months, but some of their his videos are actually very good educational videos, such as this one. And yeah, the climbing stair example is the one that really helped me uh, mm, really helped me sharpen my thinking process on how to come up with a dynamic programming solution or algorithm. And here it says that yeah, you can read the problem on top here, but yeah, using dynamic programming we can calculate on each step uh how many distinct ways that you can go or you can reach on this step. I mean, like, if you can either climb one or two steps, so previously you can be here and you can be here, right? And because of that, uh if you calculate the number of steps that you are that can possibly make you here, and then you also count the number of steps that possibly make you here, those two the total of those two is like the combination that can make you possibly in this step. So this is what it actually says lah. I mean, like, the first time I read this when Eric To explained it, I also didn't understand. So don't feel too hard on yourself if you didn't understand. I mean, like, even after reading this and thinking several times, I still didn't get it. But yeah, thinking very carefully, or just try to understand what I my explanation just now. I think that is more straightforward explanation than what I said here. Yeah, so actually the formula for the dynamic programming, or to come up with the outcome in the I step, this formula. So this case or this example is um again relatively simple, especially for competitive programmer like Eric To. I mean, like, the formula is this. And even after finishing the video and then going back to this problem, I still cannot come up with the solution. And then I go to this another video explaining dynamic programming. Why did I why did I view that video? Because, well, it it is suggested here, and it has the most views. It's as simple as that. And actually, I didn't watch it the whole thing. I just go to the I just read the introduction. I mean, I just watched the introduction, and yeah, there's a new information about dynamic programming that I learned, which is by whom it was invented. It's by Richard Bellman, 1950. Well, after that, the video also explains that dynamic programming is is about pattern recognition, and thankfully we humans are very good at pattern recognition. And when it goes to this example, I mean, this is the exact example as the one that is shown here. Yeah, this is Fibonacci, and this is also Fibonacci. And so I didn't watch the whole example for Fibonacci, and I didn't even continue it to watch the video, but I will after this my stream. But and then it's also because I I really want to finish this problem before midnight, and by the time I watch this video, it's already 11. um I think it's 5 minutes or 10 minutes past 11 p.m. So and this is a two almost 20 minutes video. I don't want to waste, not really waste, but I don't want to sacrifice 20 minutes, and that would result in me having less time to think of this problem. I mean, like, so let's finally let me finally explain the thinking process of this algorithm, how it works. So, like I also mentioned, dynamic programming, or my intuition is to to calculate the outcome in a specific position based on outcomes of previous positions or states. Yeah, there are so many things there are so many ways you can call uh, the variables that you consider when building the deep dynamic programming outcome. But uh, what we are interested in this problem is actually the number or the length of the longest strictly increasing subsequence. So this is the outcome that we want to calculate for its not for yeah for the whole array. But uh but because uh I mean, like, the intuition is like this. If let's say the array is only two element like this. So if we already have an array of this zero, and then we add another array, another element which is one, well, uh this one, uh the longest subsequence for this index is actually one plus one to the longest subsequence in the previous uh of the previous of the previous elements, yeah, from the previous indices. For example, if we only have two elements, so this the zero index, we know that here the longest increasing subsequence is actually zero. But now, when we calculate the longest increasing subsequence for the first index, we look at the previous indices. Like, uh, we check whether this one, the new element, the latest element, the current element, whether it is bigger than no, if it's yeah, if it's bigger than uh, God, see, I cannot even explain my thinking process because I also don't know how I came up with this. Like really, almost feel like magic. But the intuition is there. Like you check each indices, no, each index. You check for their uh longest subsequence in each index, and if uh if uh the current number is actually bigger than the number in the previous index, and also well, I'm reading my algorithm while explaining, but yeah, I shouldn't be doing that, but I really forget how I came up with this. So uh where am I? Okay. uh when we go through when we go through all the previous indices before this element, and then we find that one is bigger than zero, we check whether the the longest subsequence here is actually equals uh is actually um is equal to the dp count here. I mean, like we initialize all the count to be one because we basically assume that all element have has the has a one length of the longest increasing subsequence. So if this is one and then this is one, but we actually know that one is more than zero, right? So this uh in this element, uh the longest subsequent is actually not only one but zero and plus one. So here the longest subsequence in this element is two, and then afterward we check all the subsequence, or no, we check for all the longest possible increasing subsequence in each index. So if the first index, we know that the longest increasing subsequence has length 1, then for the second index we has length 2, the maximum is 2, so the answer for this array is 2. But let me show the original array. And if we apply the same algorithm, when we move to this 0 to this index, we know that this is 1, right? The longest increasing subsequence here. Here it is 2. Maybe I should put uh, the 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 stored outcome. Yeah, this is basically what dynamic programming is. This when we store the outcome from previous situations, states. So here, the first element is 1, the longest increasing subsequence. The second element is 2. Now when we calculate here, we check whether 0 is larger than 0. No, actually not. Whether 0 is larger than 1. No, it's actually not. So we initially we know that the longest subsequence here is 1. Remember, we initialize all the element to have the longest subsequent of length 1. Now we move to the next element, which is 3. Now again, we see each element before the current element, and we see we look at the longest subsequent, uh the length of the longest subsequent in each index. Now, we know that the first index or the zero index has length 1, or the longest of its longest subsequence. The first index is 2, second index 1. Now, for the current element, which is 3, we compare to to the number of the previous element. What I mean is like we compare 3 by to 0, and we know 3 is bigger than 0. But and then the current dp, or the current outcome for this element is 1, right? Initially we know that if we consider this as the last element, or the only element, this is the longest subsequence actually has length 1, its own self. But we know that there is 0 here, which has one longest increasing subsequence, which has 1 as its length of the longest increasing subsequence, and 3 is bigger than 0. So 3 can have in this position, we can increase 1 from its previous value of the longest increasing subsequence. You know that initially it's 1, so we increase by 1, becomes 2. Basically we add 1 because we know that previously in the 0 index, it has a long it has a length of 1. But because we introduce a new element, which is 3, we have we now have 2, uh a length of 2 of the longest increasing subsequence. And then we go to all the subsequences. I mean, we go to the next elements as well, until just before the element just before our current element. And things got interesting when we consider the first index, because on the first index, which has number 1, we know that the longest subsequence here is 2 already. And but and then we check that 3 is actually bigger than 1. So because 3 is bigger than 1, and we know that currently in this position, our longest subsequence is 2. I mean, like because because just now we checked from the 0 index that this first element 0 has 1 length. So we increase by another 1, so we got 2 here. But when we see here, this is also 2. I mean, like but we can still but 3 is bigger, like strictly bigger, strictly bigger than 1. So we can introduce 3 as a new as the as part of the longest increasing subsequence. So actually in this situation, for this index, the length of the longest increasing subsequence is 2 plus this new element, so it equals 3. I mean, like 2 plus 1 of the one one element, which is bigger than the previous possible longest increasing subsequence. So this is 3. And so if we well I think this video will run very long if we go through each element here. But actually if we go to here, uh we can see the dp count, or not the dp count, like the outcome, the longest increasing subsequence in each index. Like for example, for this array, uh just like I simulated just now, the first index has the 0th index has 1 longest increasing subsequence. This count field is the length of the longest increasing subsequence. And for the second element, 2, just like this, 1 2 1 3, this is also 1 2 1 3. And when we move to 2, the count is 3. And when we move to 3, now okay. Now, uh, I almost I'm almost stunned by my own deduction in my mind. But actually, this uh, when we go to the last number, which is 3, here it checks the DP, or the longest subsequence in the previous indices, and then it found that uh, for the element just before the last element, it has the number 2. The count of the longest increasing subsequence is already 3, the length of it. So but the last element is 3. 3 is strictly bigger than 2, so we can increase the number of the element in the longest increasing subsequence. So it becomes, when we calculate the longest increasing subsequence for this, we know that we can increase 1 from the previous, from this element before. So the longest increasing subsequence is 4. So yeah, uh I mean, like, and finally, after we calculate all the longest increasing subsequence for its index, we just find the maximum, and it coincidentally, uh we found the longest increasing subsequence uh is has the last element as its last element of the longest increase. I don't know whether it makes sense what I just said just now, but anyway, yeah, this console log is actually for me to debug my algorithm, and this one is actually my assumption previously, that I think that the last element should have the longest increasing subsequence, but actually it's not necessarily so. I comment this out and choose to just get the maximum of the count from each and for the case 4, open the raw file here, raw uh log. We can see that it actually 6. This happens in the last element. I mean, like, for example, where's the so this 6 again. I don't want to uh go through the algorithm again, but I just want to point out that this 6 this subsequence, minus 24, 2, 3, 5, 6, 35. There are 6 elements. So that's it. I mean, like, uh yeah, there's no project update for tonight, but uh this counts as a, a part of my resolution in being consistent in uh, problem solving or solving problems. So and my way of doing it is just by doing lit code. I never do lit code as diligent as this year, and I hope this 5 day streak will continue tomorrow as well, and for the rest of the year. Uh, yeah, before this year, I only did one lit code problem, an easy one, I guess. No. You can go to the problem. You can see the problem. You can see the one that I solved. Yeah, these two sum and add two numbers. Oh, I actually already solved quite a lot, but yeah, I think many of them are easy problems, right? The medium one is the one that is that was in the daily challenge for this year. So especially this one, man. I'm really happy that I got to dynamic programming for the first. Anyway, well, thank you for watching this stream. I think that's all for tonight. Tomorrow I need to wake up early to clean up my house, do some grocery shopping with my wife. And again, if anyone watching, there's one person watching. Anyway, thank you for watching, and see you in the next stream. Uh, I hope I can bring you more updates to my projects. Especially Ruang Baca. I mean, like, I haven't updated it this year, so maybe tomorrow. Or yeah, this is actually already 6th of January now, so maybe today. Again, thank you and see you next. Bye.